Okay, we are live. Hi. Whole bunch of research to do today. Whole bunch of research to do today. Get Restream up. Let me get the graph from last night's experiments up. And I will talk about what I'm going to do today. Quick outline of the schedule. And then we'll start on the first block of stuff. So first thing, not a terrible result from last night. Let's see. So this is, it looks a little weird. The curve on this was a little weird. This is neural MMO. This is 30 billion steps-ish. Yeah, 30 billion. 20, was it? It says 22 billion steps. Ah, right, 22, 23 billion steps. We've got this curve. We've got this curve. Oh yeah, we got this curve. Where's the good baseline run is my question. Not this one. We just have to find the actual good baseline. Yeah, that'll do. This one's pretty good. So, this is from before we fixed the bug, right here. And this was a slightly different one from as well before we fixed bug. And now we have this one. So it's a little less smooth than this one here, but this still looks like it has potential to do better longer term. And this is a pretty early version of the new code as well. So I think this is not bad. Yeah. So at the very least, we fixed the bug that was like absolutely breaking everything. So here's the plan for today. I have a few different topics that need some work. There is an experience buffer. We came up with a pretty decent optimization to the experience buffer to implement. I want to look at on policy versus off policy methods from a number of angles that aren't typically looked at, because I want to really get a sense of why you need longer trajectory segments for on-policy learning, and if that is actually true. That's a major thing. There were a few other things as well I was thinking of today. Oh yeah, there's the diversity is all you need stuff, exploration algorithm. We have some experiments to run there. And if we get through all of that, there's also some binding stuff where we can work on making it way easier to interact with and write various types of sims with Puffer, because there's some curriculum learning work that we've been looking into on that. So that's roughly what I have planned for today. I think that, I feel pretty fresh at the moment. We can start with like the heavier research stuff. Schedule-wise, it's probably going to be, I work on this for about 2 hours-ish. I get breakfast real quick. I come back. I work on that for another 6 hours or whatever, 4 to 6 hours. Quick dinner break, come back for another couple hours. And, we'll see. Hopefully we're live at least 10 total hours today. That is the goal. At least a good 10-hour workday for a Saturday. That's like baseline solid. Okay. So first thing I want to do, I want to compare this thing here. I want to see if these have like times. And a shot. Welcome. Let's go to make it review mode. There we go. I gotta actually get like a decent stream overlay at some point. I do plan on actually, building out the stream stuff and taking that a little bit more seriously. This is kind of a cool thing. All right, so this is the plot from Rainbow originally. They have one for Atari in here. Morning. The PPO paper did include full Atari results, right? This is Atari 49. This is 40 million game frames. So the original Atari, or the original PPO paper, only has 10 million time steps, 40 million frames. So this is a tiny, tiny result. So this is going to be apples and oranges here, unless they give us. I remember sometimes the DeepMind folks give you tables. They give you an ablation table, but this is from 200 mil. Okay, so presumably this is 200 mil. You see like breakout or something? Actually, this is kind of funny. So rainbow on breakout doesn't do as well as distributional DQM. This is like 400 score or something after 200 mil frames. What did they get here? I want to get like a direct comparison of rainbow to PPO score-wise, but also like compute-wise. That's the first thing I want to do today. Okay, yeah, so here they get, this is only 10 million train frames, and they're at 400 here, right? No, that's Acer. What's PPO get? 300. That matches CleanRL roughly. Well, CleanRL matches this rather. Like 300. Which is pretty darn close to this thing, actually. 10 million frames would be like over here. Now, the question is going to be, I want to see how many times they use each sample. If it's something ridiculous. $7 million frames in 10 hours wall clock. That's got to be really slow, right? Do they have an algorithm block? The value of n in multi-step learning is a sensitive hyperparameter. So n equals 5 does worse than n equals 3. So literally, they take into account three-step trajectory segments. It does worse if you go any longer. But see, what I want to learn, or what I want to know here rather, is how many times on average they're using each sample. Let me see if I get the clean RL one. Clean RL just added Rainbow 4 days ago. Target network. Number of atoms. Okay. So how does this thing work? Global step. So this is epoch, I assume. And then they should step the M somewhere in here, right? M's reset. They get actions. And then they step the M. And then they have train frequency. Is this on parallel M's as well? So let's see, train frequency. Four. So every four samples they train. Env. Num M's. It's going to be like 8. It's 1. Literally 1. 1 environment. Holy. Well, that's useless. Okay. So every 4 actions. Yeah, a single environment only. This is insane. This thing, my guess out of the box, just based on that, is this thing is probably, I'm going to say like 200 steps per second. So that's like, the Puffer implementation for PPO is at least 20,000 on the same Atari environments. And if you use our version of Breakout, Pong, and Enduro, then you get like 2 million. So RL research was really something back in the day. Like, see, the trick here, right, is all these papers, they report frames as the x-axis, and they say, well, if we just keep the same number of frames but we get better score, that's better. And they'll use like 100 times the amount of compute. So yeah, there's a lot of weird like academic posturing, like saying, oh yeah, we controlled for the same variable, but they control for variables that just do not matter. It's really dumb. But basically what I'm trying to figure out right now is how much more compute Rainbow used versus PPO, because I want to get a sense of whether this algorithm actually does anything. Like, are there good off-policy algorithms in general, or is this just like people controlling for the wrong variable and all these algorithms actually suck? So this is 4 steps. And every 4 steps, sample args.batch size. $32. That's not terrible. That's 8. So that's on average 8 uses per sample. It's prioritized experience replay. So it's not actually going to be like an even 8, but average of 8 reuses per sample. So that should be about twice as many steps, I believe, as PPO does. But you also get prioritized experience with this thing. Are there actually like good baseline curves on Rainbow anywhere? Oh, this is Minchi. Shoot, they have this on. Oh, come on, guys. They got PPO and DQN. They have any real algorithms here? Not a single real off-policy algorithm was used. Also, they're doing something really weird if they're seeing DQN doing better than PPO. They're doing something really weird. Oh, dang, I was looking at this. Why did this get rejected? Huh. Now stuff is getting rejected for being on Atari. But it wasn't on Atari either. I'm very glad to no longer be publishing. What is your favorite thinking principle or philosophy? Wait. Concepts or philosophy programming? Are you asking me what my favorite content is? Philosophy content, or are you asking me something different? Okay, so this is 12 hours is what he got on this. Let me see what my implementation would get. So that's the baseline. So 200 million frames. That is 24. Was it 12 hours? Okay, so this is 4,000 steps per second. So 4 to 5 times slower than Puffer. But we can't say without access to the implementation whether they're using 4 to 5 times more samples or if it's just a slower implementation. We should see that. They had this on modern games as well. Yeah, that's ridiculous that this gets rejected. There's really no point in being in academia in RL. Can we figure out how many steps? You know, it's weird that they still don't solve breakout, right? I guess I'm comparing, though. It's not entirely fair. Our version of breakout's a little different than the Atari one. I think this is still better than Rainbow, right? Wait. That's weird. Wait, Alien? Break it. This is misreported. Wait. Isn't that misreported, or did I misread something? Rainbow's in black. My guy, you misreported the baseline. It should be up here at least. Higher, right? Yeah, that's like close to 400. Okay. Let's just check Pong, or Pong should be 20 in both, right? Okay, Pong shows 20 in both. Let me pick one other one. Where's Enduro? Okay, so Enduro here is 2. And they report Enduro as also 2. Okay. So there's some weird misreporting in here. But I think that they had the overall as well, right? So this was 200 mil frames, IQM. This is mean human normalized performance. Wait, wasn't the original higher than that? No, just over 2. Yeah, that looks like it's just over 2. Okay. So there's some small inconsistencies, but I think the mean result is about the same. This will be good for ablations, actually. Can we find out how many steps they trained, though? Each sample. That's what we need right now. Frame stacked. Yeah, that's normal. It's funny they're still not using LSTMs. Training for 200 million frames is equivalent to training to 50 mil steps. Okay, good. So they did this correctly then. Yep, so this guy actually does some responsible research. Cool to see. But, oh, and they have 64 M's. What are your thoughts on TD-MPC2RL algorithm? Never heard of it. What is this? This is world modeling. What's this baselined against? Didn't control, Maya suites. Mostly robotic stuff, which is why I probably haven't seen this. They have this versus Dreamer v3. Okay, that's something. So we do have a published paper on studying some of the stuff in Dreamer v3, and it did not hold up at all. But I think that they are not... Hold on. This is steps. Do they have wall clock? They have model parameters. Oh, this is massive. They're training ridiculously sized models for the task of this. That's funny. $33 GPU days. Holy. So what did I say like 20 minutes ago about people just messing with the x-axis a bunch? I'm pretty sure the Dreamer ones was like a day, and that was already a lot. Yeah. I don't know. I want to do some stuff in world modeling, but just like papers like this really don't do anything for me because they're controlled for completely the wrong variable, and so you can't really compare them to anything. Like literally nobody cares about this variable at all outside of academia, and everybody controls for this. Like nobody cares about steps. The only time you care about steps is if you have a slow simulator, and then you still don't use it as the x-axis. You still end up with wall clock time, and you're just constrained to the speed of that simulator. Hang on, this is a 64 batch size. Gradient step every one vex step. You take a batch size of 256. Replay ratio is 1/64. How does that make sense? They do multiple batches or something? Gradient updates to environment steps. taking one step in 64 environments with one gradient update. How does that give you 1 over 64? Am I dumb? One step in 64 environments and one gradient step with a batch size of 256. Taking multiple steps in parallel, and performing updates on larger batches can significantly reduce wall clock, obviously. One step in 64 environments with one gradient update with a batch size of 256. This results in a replay ratio of gradient updates to environments up to 1 over 64. That doesn't follow, right? It's 1 to 4. This is actually then the sample, if I'm reading this correctly, this is the sample reuse, the same sample reuse as PPO defaults. The only difference being that it's prioritized replay. This is 8 hours on ProcGen. So this paper seems more fair. And he got this working on like some pretty real tasks here. Okay, so here, they should have some ablations, right? Not recurrent. Ablations. Man, it's like nobody ever benchmarks versus like on policy only benchmarks versus on policy, off policy only benchmarks versus off policy. You don't need to benchmark model based versus model free, but on versus off would be nice. They've got this massive range, but it's clearly way out here. Okay, this is a parameter difference. I think that's some even decent graphs on this thing. Here it is, right? So max pooling, whatever. I assume without Impala, they mean the architecture. Munchausen? What is this thing? Oh, they also have dormant neurons. Let me see this one thing that they added here. What is this thing? Okay, I might have to look at this thing. Let's go back to the ablations. Because that wasn't all the different things that they threw on it yet. The fact that they're listing Impala, though, is the biggest thing. Presumably they mean the architecture. I'll have to see what that is. Yeah, so this is the Impala like architecture, this sort of conv block structure. So whatever this thing is, I have to look at the math, and then Impala are the two big ones. My guess would be the Impala CNN. Yeah, I would assume so, right? Because like Impala was more than just the CNN, like the architecture. Like the main actual thing from Impala was that it was this asynchronous like infrastructure setup, right? And then I think they threw vtrace on stuff to correct for that. But then they also happened to throw in this like way better architecture. And then everyone says that, oh yeah, we use Impala, but they just literally mean like the model def and not all the rest of it, right? Welcome as well. Okay, here are the ablations, right? Oftentimes DQN people use the Impala CNN or the nature CNN. Yeah, and it makes it really tough to compare. So basically what I'm trying to figure out now is apples to apples. How well does off policy do versus on policy? I'm trying to see if you can actually find that. If you can find specifically what things in off policy are responsible for working at all. And then the other thing is that like these off policy methods seem that they only bootstrap over like 3 steps or whatever. That's their effective horizon is 3 steps. And on policy doesn't work unless you give it like at least 32. So I'm trying to figure out what the heck happened there. Because we have this like prioritized experience replay buffer now in PPO as an option. And it works if you just use it over data from the current epoch. But if you try to use stale data, then you mess up the value function. And yeah, I'm trying to figure out if we can steal some stuff from off policy without all the baggage that comes with it. Joined a bit late. Thanks for welcome. I will be live here for probably 10 hours today, minus meal breaks. Welcome to Puffer AI Deep Research. Except instead of just typing stuff in a language model, it is me sitting here and reading papers and writing code all day. Wait, so, okay, this is not performance. They've got dormant neurons. Isn't a problem. They've got rank, weight norm. None of these tricks have any impact on anything other than the smaller models being like higher, constant. Wait, where is... Let's see, churn. They actually did some good research on this. Hang on. This got rejected. Man, reviewers are really dumb. What are they looking at here? Policy churn? What is policy churn? Action gaps and action swaps, which can cause excessive off-policiness. Oh yeah, so the other thing I kind of think I figured out the other day, so if we have any RL folks in the chat, then maybe folks will have some idea on this. But one of the really, really major tricks in Rainbow that is now also being used here is multi-step learning. And they have this defined right here. So this is literally just discounted returns over the next n steps. And this is literally like, this is the same as what is used in generalized advantage estimation. It's just discounted returns, bootstrapped returns, except they only bootstrap like 3 steps. And they say it works worse with 5 steps. And if you look at their ablations, this matters as much as anything else in Rainbow. Like if you just take that out and nothing else, you crash the performance. This is no longer valid for off policy though, right? Because off policy, right, you're assuming that you have your Q function at one state, which means that you know you know the value if you take any action to get to the next state, right? But if you put 3 steps in the middle, then you no longer know the reward that you're going to get. Like you no longer know the value of every possible like intermediate set of actions. So like the way that off policy learning is set up to handle off-policyness doesn't work anymore with this. I'm pretty sure. Which is why I think that this, like, they bootstrap 3 steps forward, because obviously you need to bootstrap forward. Like, you need to not be training on single step bootstraps, but they kind of just break the math and they just do it anyways. So I don't think off-policy learning actually works with off-policy data because of this thing. So I think this is kind of just as much of a hack for off-policy as like clipping is for PPO with on-policy. Where'd the paper go? Is this BTR? Wait, did I lose the paper? PPO. Where did the BTR paper go? Oh, here it is. Do we have they got nerd sniped by dormant neurons? Layer norm, nerd sniped. Doesn't help. I hate layer norm. It helps a little bit overall on Atari 5, but Atari 5 is not a great benchmark. See, it's worse on like this end a little bit. It's less stable. Oh, so no sticky actions. Wait. This is something that I said, that sticky actions were dumb. I have an article on this on X. On par with everything, pretty much. Slightly better here. No point in using sticky actions. Does better with life information? Okay. That's kind of interesting to know. Did we miss the rest of the ablations, or do they not happen? Oh, apparently I'm wrong. Apparently layer norm is slightly better. Okay. It's only on Atari 5, but it is for, yeah, every single task. Was I reading the wrong one? Yeah, okay, this is the right graph. Okay, layer norm is... Yeah, it's actually kind of okay. Where did they put the layer norm in? Wait, did they say where they put layer norm? I'm gonna ask the author where they put layer norm in. They don't have it in here, right? Yeah, they don't have it in here. I mean, I guess I'm really only opposed to layer norm because it's slow. Can't you fuse it? You could fuse the kernel with a linear layer, can't you? There should be some way of doing that. Let me find the rest of the ablations. Are they in the main text, maybe? They report this, but they don't report... Wait. Oh, here it is. I'm done. Yeah, right here. Boom. This is exactly the graph that you want. Now, they only have this, it looks like, on Atari 5. We'll have to just have that be a thing. So, no Impala, I assume, is the architecture. That's the biggest one, right? No Munchausen. Munchausen? I don't know how to pronounce this thing. That also looks pretty big, right? Broken, broken, broken. Okay. And then the other one is the baseline, Rainbow Impala and vectorization. So literally those two things are what matter for this the most, like way more than anything else. Architecture and then Munchausen. And then I believe if we looked at the rainbow ablations, the things that mattered the most for these were no multi-step, prioritized experience replay, and distributional RL here. Removed double. I don't see distributional in here. N-step TD learning. Don't talk about the distributional thing. But this thing actually looks like it matters. Is there a site for this? Yeah, right here. Is this even a common paper? Did this guy just find this thing? No, this is like some super random paper this guy just found that made a huge difference for him. That's a Google Brain paper, but didn't really get much attention. Did they have good results on this? They do. And this is actually compared to Rainbow. But they don't get as impressive results because they don't put this on Rainbow. Right? Okay, let's actually take a second to understand what the heck this is and if this what this actually does. So first let me read their thing on this. Also, let me just open Discord for 1 second because I think I know somebody who knows the author. What is this? What is this thing? This is where I attempt to understand math that I did not actually study. Bootstrapping is a core aspect of RL used to calculate target values, with most algorithms using reward. Okay, except that it's multi-step, right? The optimal Q value of the next state. Yeah. Optimal policy is not known. The current policy is used. Kausen looks to leverage an additional estimate in the bootstrapping process by adding the scaled log policy to the loss function. Why is that a good idea? Kausen does not use an argmax of the next state. Double DQN is obsolete. So the update rule is you add some constant times log of the policy AT given ST plus, what is this sum? Oh, sum over actions. And then this is the same estimate, right? So you subtract out this term from all the actions, and then you add it to the one that you actually select. Do we have anything that looks like this, though? Does this work for on policy at all? Let me think if we have anything analogous, like Q of ST up. This is the update rule. With the update rule. Is this for like tabular or something? I don't understand. Let's see how they introduce it. Add the scaled log policy to the immediate reward. Wait, our core contribution stands in a very simple idea, adding the scaled log policy to the immediate reward. It's competitive with distributional methods on Atari games without making use of distributional RL, end-step returns, or prioritized replay. So they use this with IQN to outperform Rainbow. I'm kind of down to jam some math today. I'm sure I will bore everyone. Yep, there goes the viewer count. But I'm down to jam a little bit of math. Do they have any reasoning for why this is a good idea anywhere? Oh, wait, we do need to read this. Okay. Most RL algorithms make use of temporal difference learning in some way. This is true of on policy as well, with generalized advantage estimation incorporating that. It's a well-known bootstrapping mechanism that consists in replacing the unknown true value of a transiting state by its current estimate and using it as a target for learning. Agents compute another estimate of learning that could be leveraged to bootstrap RL, their current policy. Reflects the agent's hunch about which actions should be executed next, and thus which actions are good. Wait. That's what the value function is for. But the value function just tracks the policy. It doesn't contain information about the action distribution. Okay. Optimized for the immediate reward augmented by the scaled log policy of the agent when using any TD scheme. We insist right away that this is different from maximizing entropy, from maximum entropy RL, that subtracts the scaled log policy to all rewards. It aims at maximizing both the expected return and the expected entropy. A reference to the famous passage, The Surprising Adventures of Baron Munchausen, where Baron pulls himself out of a swamp by pulling on his own hair. Okay. I was wondering if this was some guy's name. That's awesome. I don't think I've heard of any of these guys. When is this? This is like a quiet 2020. This is like some quiet NERPS paper from when NERPS was super crowded with RL before the DeepMind merge, right? So these guys just probably didn't get any recognition at all for this. Like 100 sites on this cool thing. That's rough. DQN does not compute stochastic policies, which prevents using log policies. Wait, DQN does not compute stochastic policies, which prevents using log policies. I guess it doesn't, right? I guess it depends how you're looking at it. It can sample from the Q network, right? Well, PPO does, so we can really easily, we can do this in PPO, right? Because we compute stochastic policies by default. So this thing overtakes C51. We provide strong theoretical insights about what happens under the hood. Implicitly performs KL regularization between consecutive policies. Oh. That could help for, wait, that could help, right? Because in PPO, we do a KL clip, but we don't have a KL loss, right? What's the default PPO implementation? I'm pretty darn sure there's no... Wait a second. We just clip by KL, right? We don't actually add a loss term with KL. Where's our KL? Where's our prox KL? So look, in PPO you compute this approx KL, but you only use this to clip the policy. So you don't actually have any KL regularization added. I mean, we could easily just KL regularize, to be fair. This thing, they say it does it implicitly. Well, isn't there a form of KL, no, there are two forms of PPO, right? There's the weight clip and the KL clip. There's never a KL loss. Doesn't TRPO do that, though? I haven't looked at TRPO in a long time. We show that because this regularization is implicit, it comes with stronger theoretical guarantees. Ooh. Okay. We're not reading the MDP background. Standard RL agent maintains both a Q function and a policy. We have a value function, but whatever. So the only thing I'm not sure about this, so this is kind of an improvement to bootstrapping, which is like one-step bootstrap, which is what's used in DQN. We have a way better bootstrap in online RL because we use whole trajectory segments, right? We use like 32, 64, 128 length segments. But there's also implicit KL, apparently. Okay, so this is just DQN loss here. So reward plus regressing the target. Yeah, so this is going to be the same as the one step in here, right? Right here. So here's your one step, right? So if you set lambda equals 0 in JE, you get this target here. And if you look here, so this is reward plus gamma VST plus 1, right? So here's reward plus gamma. What's this? This looks different. Well, your value function is over all actions, right? It's over the actions of the current policy in on-policy learning. Here, they have to sum over the policy evaluated on all actions, because Q function as a value Q function contains the future value depending on every single action that you take. So this is kind of the same thing, right? We modify the regression target. MRL assumes stochastic policy, while DQN computes deterministic policies. A way to address this is not only maximize the return, but also the entropy of the resulting policy. that is adopting the viewpoint of max entropy RL. Whatever. We throw in entropy bonuses, max entropy is really stupid. Like, entropy is just a really dumb metric. I don't understand the people that say that this is a good idea. Like, whoop-diddy-do, your policy behaves noisily when there's nothing else to do. That's a really bad exploration method. It's straightforward to extend DQN to this setting. We call the resulting agent soft DQN. Okay, so this thing here, we don't need to care about this, I'm pretty sure. Nothing more than the most straightforward discrete actions version of soft actor critic. And we don't need this, because we already get stochastic policy as non-policy learning standard. The last step is to add the scaled log policy to the reward. Man, how does this do anything? Like, really? This is the opposite of max entropy, isn't it? Isn't this just telling you to be confident about your predictions? What does this thing do? Do you possibly, like... Do you, like, crank up your entropy bonus and then also do this? Hang on. So this is... DQN. I'm gonna have to look up the distributional RL stuff as well, aren't I? And there's a bunch of theory. Let me get their hypers first. Maybe we'll just go implement this and see if it crashes everything. Where are their hypers? And then IQN is the thing that takes this over the top. Okay. Does worse on Montezuma's, elevator action, venture. Everything else is fine. Does way better on asteroids. I wish we had asteroids. I'm surprised nobody has done that by now. It's like a pretty nice environment to implement for Puffer. Where's Breakout in here? Beam Rider. It's another one that we don't have yet. We'll try it on Breakout. We need the hyperparameter they use, though, don't we? They probably just have it inlined instead of in a table. So 0.03 alpha equal 0.9. So hang on. It's alpha tau. So it's 0.03 times 0.9, right? That's what we'd use, 0.027. Yes, I did just use Python for that. Subtract 10%. All right, let's do, I mean, this is like a one line change, right? Two code windows open. So we'll do use Manhausen. How do you spell this thing? Munchausen. False. Seven. And that's all we need, right? So before we clamp, this is config. Yeah. Where are logits? It's literally just logits of actions, right? Torch.log logits of actions. You just have to do a no grad, I assume. Breakout. Frame. Use. Would they have picked anything more difficult to spell? $312. That is size of tensor does not match. So we get here and shape action. Right, so it's logits star action. That's not what we wanted. How do we index like this? PyTorch, cake, what's it? Calls from row. Gather. Logits.gather. Hey, sorry, I've been sick for a while. Really happy to see you continue your live streams on YouTube. I hope you feel better. It was no fun. And yeah, I should just be pretty much doing nothing but streaming dev for the next few weeks. I'm really trying to get the next release of Puffer into a good spot. And that's mostly just me shoring up. There's some engineering side stuff, but I also want to make sure that we've, done a good job exploring algorithm modifications within reason. One. So is this it? And then the last one, 2. Looks good. Keep on. Yes, indeed. I am currently trying to get myself back into peak condition after. I mean, pneumonia was at the start of the year, but I'm still not quite back to peak yet. That's still going to take some time. So, action, props, this logits. I can do this as selected action. There. Okay. Isn't this going to give you a negative number? Wait. This is going to blow up, isn't it? Yeah, this is going to blow up instantly. So do they want you to select the probabilities? They probably want you to softmax, right? Pi is probably action props. Okay. So this gives you log prob. Oh, can I not just take log prob of action then? It is log probs, right? Just add log prob of action. But I probably messed that up. Hang on. Wow. Yeah, so that's flattened. So we need to change this. Sample logits. Log prob. dot t. I think we can just do this, right? The heck is this? Wait, do these things just have .log prob? Or is that a distribution? Log prob. Yeah, no. Yeah, no, this is for a distribution. Wait, what's this? Wait, why is this logits minus log sum x? This is probably screwy optimization stuff, right? This is PPO. Let's see how they do this here. Okay, log prob here. So they get action and value. Okay, so we can just do it like this. Categorical.log prob action for now, right? And then I can ask how we optimize that later. Because all this was to optimize that stuff. Because categorical's kind of slow, I remember. This to be categorical. Torch.distributions.categorical. And that works, right? Yep. Except something's wrong with that. So this gives us log prob of action. This one should be different, shouldn't it? No. It could just be log. It could just be a log thing. But I think that that's right. All right. We can always test this after a little bit as well. Let's just do. Let's do this. Let's just do Neptune. Grab my key from this. What are you doing over here? Falling off a bit. So this should match the previous curve. This is just the baseline. We're expecting a reasonable enough solve. It's 9:49. I should order some breakfast soon. Okay. Runs. We'll let that finish eval. We'll run the other one and we'll see. And let me figure out what I'm going to get in the meantime. I don't even know why I'm doing this on my phone. Doesn't look like it got quite the same result there, right? Check one last thing and I'll be good. So here's the curve. Why don't we look at like entropy? This gets you lower entropy. That's kind of expected, isn't it? Am I misinterpreting it, or is this thing just literally telling you to be confident in your predictions? Let me just at least try one last thing, cranking it up. And then we'll sanity check some stuff as well. OF. Okay, we crank the entropy up a little bit. Actually, that's a bad idea. They missed a term. This thing just missed a term, didn't it? Yeah, it missed a term. It has OCR, doesn't it? I don't see any red text. Yes. Does that make any sense to you? It doesn't make any sense to me. So this is about the same. So now the entropy matches, right? We matched the entropy, but the reward doesn't do any better. Does anybody have any idea why this thing would work? Would this coefficient be different? Doesn't make sense to me that this should help, right? I'm just trying to sanity check stuff. That's kind of all I use Grok for. It's like, am I just missing something really obvious, or does this algorithm make no sense? I mean, I could do 0.01, right? What if I do like this? Do this, this. This is what policy gradient does, though. Can be interpreted as a form of KL divergence regularization between the current policy Oh, I think that this might be off policy specific, right? Or alternatively, you might need to recompute this term. Right, you might actually have to recompute this bonus in the training code. So it's possible that this is not like, you can't just add it here. Hang on. So if you were to add this thing, instead of where you get the rewards the first time, right? If we were to add this thing when we compute the loss, no, that's worse, isn't it? Yeah. I mean, maybe. Does that even make sense, though? The way it's described in this paper, hang on, I'm not so sure about that. Doesn't this seem like this is not just added to the reward, right? This is added to the update. I actually think that this is added to. Hang on. So if you add this to the update instead, right? You end up giving a bonus. Yeah, it just ends up as implicit KL regularization, right? I think it just ends up as implicit KL regularization. Why do they say this is better than explicit KL? All right, I'm gonna use the restroom real quick, and then we're gonna review this math and see if this algorithm makes any sense. 1 second. Let's see what their math says. Does this make any sense? Yes, this is just an alternate way to do KL kind of then. Okay. Yeah, I'm pretty sure Grok is wrong here. I'm pretty sure that you have to apply this every update. So it would just be easier to just do KL regularization. Since we already have that, right? Maybe we go back to TRPO. Oh, this paper, everyone hates this paper, because this paper just has a bajillion lines of math for no apparent reason, right? Yeah, nobody likes this thing. Maybe we end up playing with KL, though. Maybe we do end up playing with KL off of this. Okay. We can do that real quick. I've got a little bit of time. Just here, I believe. 10, only a couple minutes. All right, we'll try one thing real quick because I want to try one thing. Where's the replay factor on this? Oh, I added this to the totally wrong branch, didn't I? Okay, we'll just benchmark new branch training. We'll add the replay factor, and then maybe we'll play with KL on that. Though actually, KL doesn't help, right? It's the value function that gets stale, not the policy. So actually, any of these like trust region based things are just bad for that, right? Kind of want to try without flipping then. Try this without flipping. So we were clipping 8% of the data before. Okay, so here's the new branch, right? This is what we have here. This is the old baseline for whatever reason. Oh, that's interesting. Do we just fail without clipping? Is that what's going on here? We just fail without clipping? That seems much more interesting to investigate, right? It does actually do something, but that's a huge difference in dynamics. That's a huge difference. Okay. We will investigate that afterwards. Basically, the goal for all this stuff is to figure out if there are any simple things we can steal from off-policy learning that would make an experience buffer more stable for PPO, just so we can use like a couple high-value trajectories, high-advantage trajectories. I'm gonna go get some food. I will be back after a quick breakfast, and I will be streaming for a whole bunch more hours today after that. So if you are interested in following my stuff, you want to help me out for free, just start the repo. We're trying to hit 2,000 stars. If you want to get involved with dev on any of this stuff, some of our best contributors came in with 0 RL experience. Join the Discord. You can follow me on X for more reinforcement learning content. We've also got a lot of fun demos on puffer.ai as well. So